Good evening and welcome to our webinar. I'm Chris McLaughlin, Secretary, Ayala Network. I have some items to mention before the presentation begins. If you have any questions, you can post them in the Q&A box below and I will pass them to Seamus on your behalf at the end of his presentation. If you wish to receive a CPD certificate, you can click on the link in the chat box below and download it from there. And this webinar is being recorded for future uploading to our YouTube page. I now wish to pass you to the Chairperson of the Ayala Network, Aidan Langley. Aidan.
Thank you, Chris, and thank you to everyone who's attending this evening, both IET members, other people, and indeed members of Engineer Ireland who are joining us this evening. So Seamus is the former head of engineering at Irish Lights, and I know he has a personal interest in the topic he's talking about this evening and an impressive depth and breadth of knowledge. So without further ado, I'd like to pass you on to Seamus, and I'll pass it on to you, Seamus.
Thank you, Aidan, and good evening, everybody. Our topic for this evening is history of radio aids to navigation. The ocean is a big place, and part of this screen has covered what I want to say. My definition of navigation is that it's a way to know where you are, to guide you where you want to go, and to get you back again. The Ayala definition is of aid to navigation, which is what we're talking about this evening, is that it's a device, system, or service external to craft, designed to operate and enhance safety and efficient navigation of vessels. That's to distinguish it from a navigation aid, which is an onboard instrument, device, chart, or method intended to assist in navigation. The key to navigation is to know where you are and what things are around you. Major developments in early navigation were the compass, the sextant. The needle on the compass always points north, which gave direction but not position. Early sextants could measure latitude by measuring the height of the sun at noon, but sailors were still not able to determine their longitude. This changed in 1761 when John Harbison developed the chronometer. Knowing the time at any position relative to Greenwich Mean Time allowed the calculation of longitude. Latitude and longitude were plotted on a navigation chart to demonstrate position with an accuracy of perhaps a few miles, which was okay for deep sea. For landfall, lighthouses provided a known point of reference and for finding harbors. The aid to navigation in this case is the sun and the Earth's magnetic field. Our focus this evening is mainly on marine radio aids to navigation, but of course these systems were widely used on land and in the air as well. It all started with the discovery of radio waves. James Clerk Maxwell, Scottish physicist, followed up on Michael Faraday's work on electromagnetism. In 1888, Heinrich Hertz made the sensational discovery of radio waves, confirming Maxwell's ideas. Marconi developed this and started experimenting in 1894. He set up rough aerials on opposite sides of the family garden and managed to receive signals over 100 meters. By the end of 1895, which was just a year later, he had extended the distance to over a mile. He came to England in 1896. Initial transmissions were detected in demonstrations at 1.5 miles, and on the 2nd of November 1896, on the Salisbury Plain, the range was increased to 8 miles. In May 1897, tests were carried out to establish the contacts over water were possible. He demonstrated a link from Lavennock Point across the Bristol Channel to the island of Holm, a distance of 3.5 miles. In December, and this thing has covered what I want to say. Yeah, 1901, Marconi used a spark transmitter to transmit and receive Morse S across the Atlantic, the first time, from Poldhu Wireless Station in Cornwall to St. John's in Newfoundland. From that time, radio quickly developed, and we've all heard of the impact of radio communications on the Titanic disaster in 1912. So development was very quick. Radar, which stands for radio detection and ranging, is a system based on the detection of backscatter of transmitted radio energy from an object. The targets are displayed in such a way that their bearing and range are continuously available. In 1904, Christian Hulsmeyer gave public demonstration in Germany and the Netherlands of the use of radio echoes to detect ships so that collisions could be avoided. The system detected ships at a range of about 3 kilometers. But at the time, the naval authorities showed little interest in this. Moving on to 1930, in the USA, Lawrence A. Hyland of the Naval Research Laboratory detected an airplane with CW radar operating at 33 megahertz. Again, the US didn't really take an interest until the development of the Second World War. On the 26th of February 1935, Robert Watson Watt and Arnold Wilkins demonstrated a basic radar system to detect aircraft to an observer from the UK Air Ministry. This was known as the Daventry Experiment and led immediately to development of radar in the UK. I think most people remember the pictures of the radar during the Second World War on the east coast of the UK. This was called the chain home. Typical operating parameters were frequency around 20 to 30 meg, peak power of 350 kilowatts, pulse repetition rate of 25 to 12.5 pulses per second with a pulse length of 20 microseconds. And in fact, there is a plaque in their memory in Towcester in the UK. Onto radar in a modern sense. The early radars, as we saw, worked at 30 megahertz. The next major development in the history of radar was the invention of the resonant cavity magnetron by John Randalls and Harry Booth in Birmingham University in 1940. This enabled generations of microwave frequencies at 3 gigahertz with a pulse power of 30 kilowatts. The combination of the magnetron, the duplexer switch, small antennas, high resolution allowed small, high-quality radars to be installed in aircraft. Miniaturization over the years in electronics has reduced the size of the equipment. Large magnetron radars have given way to solid-state, low-power transmitters, which take advantage of high-sensitivity receivers and signal processing to provide high-performance radars. Today's ships are equipped with both X and S-band radars. X-band is 9.3 gigahertz, S-band is 3 gigahertz, and each of those frequencies has their advantages and disadvantages. In Ireland, the Hilltop Radar at Mount Gabriel in Cork has guided aircraft across the Atlantic for decades. You can see from the display here on the left that the radar display is fairly cluttered. You get lots of returns from waves and such like. So a method was needed to identify specific targets unambiguously. One such development was RACONS, which stands for radar beacon. It's a type of radar transponder commonly used to mark navigation hazards at sea. When the RACON receives a radar pulse from a transmitter, it responds with a signal on the same frequency, which leaves an image on the radar display. This takes the form of a short line of dots and dashes forming a Morse character, which identifies which RACON you're looking at. You can see the RACON there, the paint on the right-hand picture. So during the 1960s, RACONs such as the Kelvin Hughes Ursa Minor and the Marconi Major emerged. These were valve-operated units, but they quickly were developed into transistorized units. Marconi sea-swept frequency RACONs were used on buoys and lighthouses in Ireland by the Commissions of Irish Lights from the 1970s. A further big step forward in RACONs was in 1980 when the Marconi company developed the X-band frequency agile RACON. In 2011, there was 22 RACONs in Ireland in use on buoys and lighthouses. And the picture there on the left shows a typical RACON in the foreground. Another step forward was in 2007 when new technology S-band radars using coherent transmissions with very low power non-magnetron transmitters emerged. But they were a problem because they didn't trigger the RACONs as well. So one result of that was that the IMO reduced or stopped the carriage requirement for S-band radars triggering RACONs in 2008. RACONs are very expensive, so to try and improve the radar return, radar target enhancers were developed by, can't remember now, Sea-Watch, the Sea-Watch units. These were simpler and cheaper than RACONs. They were uncoded transponders, and all they did was they made the return bigger. Typically, they on a class 1 buoy, as used by Irish Lights, the range was increased from 9 to 12 nautical miles. They didn't prove to be all that useful in practice, so they were withdrawn in 2009. Radio beacons were another development using radio. They transmit a radio signal that's picked up by radio direction finding systems on ships and vehicles to determine the direction to the beacon. In the maritime world, they were known as radio beacons. In the aeronautical world, they're known as NDBs, non-directional beacons. But they were the same units. Radio beacons first appeared in 1920s. The first UK marine radio beacon began broadcasting from Kinnaird Head on the 20th of March 1929. And this, in fact, was an attempt to improve on the fog signal apparatus that had been introduced in 1902. The signal from radio beacons is modulated in code so that the station can be identified. The initial concept was to broadcast radio signals to ships during bad weather, which would enable them to steer clear of dangerous areas. They transmit typically in the 300 kilohertz band. The technology is much simpler than radar, using simple transmitters and receivers with loop type receiver antennas to enable direction finding. In Ireland, the radio beacons were at the major stations all around the coast, as I've shown here. The objective was to enable ships to receive a signal from 2 stations simultaneously to provide a position fix. The marine radio beacon at Eagle Island was, I think, particularly popular with the aircraft industry as an NDB for aircraft flying the Atlantic. Since the development of satellite-based positioning systems, the importance of radio beacons as an aid for marine navigators has ceased. In Ireland, the service was withdrawn in February 1999. However, the equipment, transmitters and antennae had a second life as broadcasting stations for Dgps, and we talk more of that later. There was a whole range of specialized radio beacons. One particular one was, say, the ILS, a marker beacon, which is a specialized beacon used in aviation in conjunction with the ILS to give pilots a means of determining distance to the runway. Marker beacons transmit on 75 megahertz. This type of beacon is slowly being phased out, and new ILS installations have no marker beacons. In 1938, in Germany, Dr. Ernst Kramer developed the SON system using multiple transmitters. The SON means sun in German. During World War II, the British captured some SON charts and took them to Group Captain Dickie Richardson, who was the navigation officer for Coastal Command at Northwood. Richardson then found a receiver and tuned in, getting a good bearing on his location. So he ordered the RAF map department to mark up all the British maps. He called the system Console, meaning by the sun. The Navigator only needed an ordinary radio receiver tunable to 300 kilohertz to use the system. He heard a series of dots slowly merging into a steady tone, and then becoming a series of dots and dashes. He simply had to count how many dots or dashes he could hear before the steady tone, and then plot his position line on a suitably overprinted map. One station didn't provide a fix, of course, but it was a very useful system requiring little expertise to use and very simple equipment. In effect, Console operated like a radio compass. For Atlantic travelers, combining the use of echo sounder and Console to the bearing from Console provided an accurate position. Console was widely used in the post-war era with stations in France, Northern Ireland, 3 in the US and several in the USSR. It was one of ICAO's recommended long-range navigation systems. The Northern Ireland station was in Bushmills in County Antrim. The last station to go off air was the Norwegian Stavanger station, which was discontinued in 1991. Then we moved to a whole new era of the hyperbolic systems. A chain consisting of one master and two slaves were set up to transmit in synchronized time. Differences in the arrival time of the pulses from a pair of stations were measured and transposed to a Loran lattice chart, and position could be plotted. Loran was measured. Loran provided facilities where ships and aircraft derived their positions at quite long distances. Loran A was the first of them, started in the US Army Signal Corps Technical Committee in 1940. Ranges of 1,000 miles with at 200 miles, with an accuracy of about 1,000 feet were achievable. In practice, the maximum reliable range was 700 miles by day and 1,400 miles at night. Loran C, which I think is much better known than Loran A, was the successor, originally developed by the US Navy Radio Navigation Service for the US coastal waters. The driver was the need for greater range than provided by Loran A. Loran C operated in the frequency range 92 and 10 kilohertz, providing using pulse time and phase difference as its operating principle. The daytime range is 1,200 nautical miles, and nighttime range 2,500 nautical miles. It was first developed in 1946 with Sperry Company Cyclone system. The system wasn't fully developed until 1956, and tests showed a ground wave range of 2,250 miles and a nighttime ground wave range of 1,650. Skywave was detectable up to 3,000 nautical miles. The US Navy established transmitters along the northeastern Atlantic and the Mediterranean during 1957. In the Far East, the Chika system is the equivalent of the Loran C, and eventually coverage was established more or less right across the whole northern hemisphere. In recent years, receiver technology has driven the development of enhanced Loran in the same, using the same transmitters, but the receiver measures distance to the transmitter in the same way as GPS receivers. But however, GPS more or less relegated Loran C to oblivion. Another hyperbolic system was the Deccan Navigator system. It was unusual at the time in that it was a commercial rather than a military system. It originated in the United States around 1945, developed by the Deccan Navigator Company. During daytime, ranges of around 400 nautical miles could be obtained, reducing to 200 to 250 nautical miles at night because of propagation conditions. In the 1960s, a considerable but failed attempt was mounted by Deccan to have it adopted by ICAO for aircraft. When the service first became available, users would rent a receiver from Deccan. From the 1980 onwards, Deccan Navigator was funded by the lighthouse authorities in the UK and Ireland. Deccan was used throughout the world. At its peak, there was chains in almost all shipping lanes in the world. There was 4 chains around England, 1 in Ireland and 1 in Scotland. The transmitters operate in the 100 kilohertz band using a master and 2 slaves. The differences in phase between each of the slaves and the master could be measured by the receiver, shown on a red and green indicator. These were then transferred onto the lanes on the Deccan charts, which gave you position. Deccan developed another system called Pulsate, which was also known as AccuFix, which was a short-range Loran-C system. There was one of these transmitters at Mizzen Head for anyone who knows that area. It was in use during the 1970s through to the mid-1990s. There was other systems like HiFix for surveying, Dectra for transatlantic aviation, Delrac long-range system, and so on. Again, GPS rendered Deccan obsolete, and it was shut down in Ireland in March 2000 after 50 years. Omega was another radio navigation system developed by the United States Navy for military aviation. It was approved for full implementation in 1968. Initially, the system was used for navigating nuclear bombers across the North Pole to Russia. Later, it was found useful for submarines. The system comprised 8 CW transmitting stations situated around the world, operating on 10 kilohertz band and providing an accuracy of 2 to 4 nautical miles. It was the first truly global range radio navigation system operated by the United States in cooperation with 6 partner stations. Omega achieved full 8-station implementation in 1983 and was shut down in 1997, the end of another era. There were a number of local hyperbolic systems developed for specific applications such as fishing and surveying. Things like Rana, Toran, Salides, Deccan HiFix. But GPS replaced them all. Then the next revolution was satellite navigation. The transit system was the first of these, also known as NavSat. The system was primarily used by the US Navy to provide accurate location information for ballistic missile submarines, and was also used as a general navigation system by the Navy, as well as hydrographic and geodetic surveying. It was used for civilian general navigation by marine users, principally in the ocean phase. It was inspired by Doppler shift measurements from Sputnik transmissions on the 4th of October 1957. Development of the system began in 1958, and Transit 1B was successfully launched in 13th of March 1960. The concept is fairly straightforward. Because of the orbits of transit satellites, only one was usually visible at a given time. At the equator, this gave rise to delays between fixes that could be of several hours duration. The transit system again was made obsolete by GPS. The new revolution, I think, rather than development, occurred with the development of Navstar GPS. Pardon me. GPS is a global navigation satellite system, abbreviated to GNSS, developed by the United States Department of Defense and managed by the US Air Force 50th Space Wing. It's a worldwide global navigation satellite system and freely available for use by everybody. It uses a constellation of 24 medium Earth orbit satellites that transmit precise radio wave signals, which allow GPS receivers to determine their current location, the time, and their velocity. It was Started in 1978, the first Block 1 satellite was launched. By 1993, GPS had achieved initial operating capability. In 1994, the complete constellation of 24 satellites were in orbit, and full operating capability was declared in April 1995. As I said, it was provided by the Department of Defense in the US with a constellation of 24 satellites in 6 orbital planes. It uses a single L1 frequency with code division multiplexing. So the whole system operates on a single frequency. There was a precise positioning system for military use and a general CA system for general use. This CA system was initially provided by selective availability. In other words, they jittered the clocks on the satellites to reduce the accuracy to 100 meters, but the CA range was down around 20 meters. I should say that the SA was removed in 2000. In Russia, a separate system was developed called Gnss. It's a radio-based satellite navigation system as well. Obviously, it was developed. Our development began in 1976, and the constellation was completed in 1995. The system rapidly fell into disrepair with the collapse of the Russian economy after the collapse of the USSR. The system has been updated and new satellites have been developed and launched. So in December 2015, the system was officially completed. There are currently 28 satellites, solar vehicles in constellation, with 23 operational. Europe attempted to develop our own system called Galileo. It's a 10 billion euro project. It's meant to provide an alternative and be complementary to US GPS. It operates as a single frequency system with code multiplexing the same as GPS. On 30th of November 2007, the 27 EU transportation ministers involved reached an agreement that it should be operational by 2013. As of now, it is still in the initial phase. These are some of the launches. The initial launch was in 2011 using a Soyuz spacecraft. There are 26 satellites currently in orbit with 24 operational. 30 vehicles are expected by 2021. It remains to be seen if that will happen, but for the moment, the system is in initial phase. In China, the Beidou system was developed, started in 2009. From 2017, 30 satellites were launched. It's known as BDS-3 in its current form. It was initially a regional system, but BDS-3 is a global system, was commissioned in August 2020, providing 10-meter accuracy, velocity measurement 0.2 meters per second, timing accuracy of 20 nanoseconds, and an availability of 99%. India also developed a regional system which was designed to cover just India and 1,500 kilometers around the Indian mainland. They use 7 satellites. It has standard positioning and an encrypted service, the same as Galileo will provide, and was operational from 2018. Japan developed the QZSS system, which again is a regional system. It complements GPS to improve coverage in the Eastern Asia, East Asia and Oceania. It's a 4-satellite constellation in orbit since November 2018, and they plan to extend it to 7 satellites for autonomous capability by 2023. Give you an idea of accuracy, Omega 2.2 nautical miles, and you go down then to from VOR, DME, and Doppler aircraft systems, inertial systems. After 1 hour's operation are down to 650 meters. Then you have the satellite systems like Transit and Tacan, and the hyperbolic systems like Deccan and Loran, and then GPS with an accuracy now in down around 10 meters. The International Association of Lighthouse Authorities developed an AIS concept, automatic identification. The idea of this is that is a system that makes it possible to monitor ships from other ships. So it's a ship-to-ship communication system. AIS-equipped ships continuously transmit a short message on VHF containing information on their position, course over ground, speed over ground, gyro course heading, and so on. Ships equipped with AIS meeting anywhere on Earth are able to identify and track each other without being dependent on shore stations. This was a safety system primarily to avoid collisions in congested waters. One of the nice things about AIS is that it could be overlaid onto electronic charts. You can see it circled on the middle here. You see the workload is so small that one of those guys has his feet up on the desk. This is a chart of the Atlantic showing ships as shown by AIS. This is from a company called Exact Earth. As you can see, there's a lot of shipping, but you can appreciate the huge amount of information that is available through AIS. This is up between Northern Ireland and Scotland, showing density. So the tracks from AIS can be recorded and then plotted as a density chart like this. And this is quite a useful way of displaying AIS information for a number of different things. In Irish Lights, we used it to measure traffic and determine what aids to navigation were required in particular areas. Irish Lights have 116 stations on both lighthouses and buoys, and the transmitters can be either physical, in other words, they're on the station where they're transmitting, or they can be virtual. For example, a lighthouse transmits a signal which looks like a buoy signal. VTS is defined by Ayala as an aid to navigation. It's a shore-based system combining radio communications, radar, and more recently AIS. It's like air traffic control for aircraft, but in this case for ships. An office is in a busy port such as Dublin, monitors and directs all traffic and in and out of the port, and craft movements are tracked by radar and AIS, and instructions issued by radio communications. However, Gnss, GPS, and all the other systems are all vulnerable to system failure. Malicious interference with weak signal jamming and spoofing. You can have damage due to high power microwave signals. You can have ionospheric and coronal mass ejections causing problems in the atmosphere. We've had a case in the US in the early days of GPS where a faulty masthead TV amplifier was emitting noise and blocked out GPS for the entire port. Is there an elephant in the room? GPS has infiltrated every aspect of our lives, but what if it fails? GPS timing is even more important to us today than its positioning. Every major service that we use requires timing for control and communications. If GPS system was suddenly not available, what would happen to all these services? Position and navigation, telecommunications, power, data communications, transport and autonomous systems, entertainment, broadcasting. This has been a major concern and has led to the development of various augmentation systems. Integrity is defined by ICAO as a measure of the trust that can be placed in the correctness of the information supplied by the total system. Integrity includes the ability of a system to provide timely and valid warnings to the user when the system must not be used for the intended operation. Therefore, integrity is the probability of not using a false signal. The various mitigation systems include redundant systems like providing more GNSS like GLONASS, Galileo, Beidou, providing backup systems like LORAN-C, eLORAN, radar map matching, 3G cellular phones, DGNSS radio beacons, AIS ranging, contingency systems like lighthouses, buoys, and integrity systems like RAIM and the Ayala DGPS and space-based augmentation. The basic concept of augmentation is that the signals, the signals from satellite are picked up, say, by a reference station, in this case, say the lighthouse on the right. The lighthouse knows where it is, so it can calculate errors for each satellite. It then broadcasts on, in the case of lighthouses, on the old radio beacon transmitters, it broadcasts correction signals to ships and aircraft, mainly to ships, in order to warn them if there's a failure and to improve accuracy. So in the days of selective availability with 100-meter accuracy, you were getting 20-meter accuracy with DGPS. Space-based augmentation was provided. You have in the US the Wasp system, Europe has the Egnos system, India has Deccan, the Far East has MSAS. Looking at those in a little more detail, the European Egnos system, the European Geostationary Navigation Overlay Service, it was originally designed for aircraft using 3 satellites, provides an accuracy of 1 meter. Initially, it was started in 2005 and has been operational since 2009. Full service was declared in March 2011, and there is now a consideration of adopting it for maritime use. The WAS system, Wide Area Augmentation System, operated by the US. It's extremely accurate. It provides service for all classes of aircraft in all phases of flight. It provides a glide path which is more stable than that of ILS, down to minimums as low as 200 feet, which is lower than the VOR or NDB non-precision approach. In July 2003, the WAS system was activated for general aviation, offering 350 foot minimums. Deccan is operated by the Indian government. Its availability filled the gap between Egnos and MSAS, in other words, between the European system and the Far Eastern system. In December 2013, it was certified for aircraft use. MSAS, operated by Japan, was operational or is operational since 2007, supporting en route, terminal, and non-precision approaches. You can see Wasp, Egnos, MSAS, and Deccan there, but there are many other systems either in being considered or in development. But the four I mentioned are the ones which are currently operational. Ground-based augmentation systems like the Differential GPS System, otherwise known as Dgps, is a ground-based enhancement to GPS that overcomes the problems of integrity and accuracy that we spoke of earlier. The system operated using the old radio beacons. It was sponsored and defined by Ayala, the International Association of Lighthouse Authorities, for marine use, but was also widely used on land. The beacons operated, as I say, between 283 and 325 kilohertz using 1 kilohertz transmitters, providing integrity warning and accuracy improvement to 5 meters with 95% confidence. In Ireland, trial transmissions began in 1998. Full operating capability was declared in July 2002, and the system is being phased out next year, March 2022. The system was built in conjunction with the UK, so it was a UK-Ireland cooperation with 6 stations in England, run by Trinity House, 3 in Scotland, operated by the Northern Lighthouse Board, and 3 in Ireland, operated by Commissions of Irish Lights. And each GLA had their own control station, one in Dublin, one in Edinburgh, and one in Harwich. The system had overlapping coverage from each of the transmitters, so that if any one station failed for whatever reason, there was still coverage from the 2 adjacent stations. So this provided an availability of 99.8%, category 1 aid. You get an idea from this chart of the coverage. This was in 2001, so there were further developments, like Canada doesn't have any stations shown here, but in fact it had plenty of stations. But you can see the whole of the northern part of the hemisphere, Australia, New Zealand, very little of Africa, and only the east coast of South America. This may be the future of integrity monitoring, receiver autonomous integrity monitoring, shortened to RAIM. It's a receiver-based system using multiple constellation signals to analyze and verify the integrity of the received signal. Using at least 6 measurements of redundant pseudo ranges, that's in other words the signals from the satellites, to identify and exclude a faulty satellite. It provides good integrity but no accuracy improvement. The good thing is that it requires no additional infrastructure other than having the capability in the receiver. For the future, what is happening? You have Egnos, WAS, and MSAS currently the space-based systems, along with GPS and GLONASS, providing the first generation GNSS. You have GNSS2 then, which is the upgraded GPS to L2C, L5, L1C. You have Galileo on L1 and L2. And when they're fully operational, it will lead to GNSS2 with the capabilities of RAIM for integrity. The IMO have attempted to integrate all these services using a concept known as e-navigation, defined as the harmonized collection, integration, exchange, presentation, and analysis of marine information on board and ashore by electronic means to enhance berth-to-berth navigation and related services for safety, security at sea, and protection of the marine environment. This is far from radio navigation. It's detailed planning and monitoring for all aspects of marine vessel operations. Accurate position knowledge and global communications are key to success. Is this the bridge of the future? Trials are already being conducted into using fully autonomous ships. Perhaps the bridge crew is a man and a dog. The dog is to keep the man away from the equipment, and the man is to feed the dog. The trend in marines, the head-up display of ship operation information and navigation. Electronic view of all surroundings using radar, AIS. Accurate, reliable position from GNSS and space-based augmentation. Integrity from RAIM. We've come a long way since the humble paper chart, sextant, and chronometer. I wonder how history will judge what we are doing today. Thank you.
Thanks, Seamus, for an excellent presentation. Some questions have come in. A question from Sean. Is Galileo in operational use at present?
It is in initial phase. It's not. They have not declared full operating capability. They're effectively at IOC stage, but they're vastly behind. Originally, I think the system was supposed to be fully operational in 2012 and then 2016 and so on. And they're now saying 2021, which is this year. It remains to be seen.
A question from John Ging. For some of the technologies, the range is substantially more at night than during daylight, whereas for others, the opposite applies. Is this tropospheric ducting or some other phenomenon?
It's ionospheric reflections. So you get a ground wave, those old hyperbolic systems operating around 100, 300 kilohertz, particularly 100 kilohertz. They're basically ground wave systems. So the timing and so on is meant to be measured from the ground wave signal. But you also get a skywave signal reflected from the ionosphere. And that upsets the timing and reduces the accuracy. If the system is generally degraded considerably through nighttime. With the Dgps system that I spoke of, that used for marine applications, the nighttime range was, I'd say, about 75% of the daytime range. And in fact, it was the range of the transmitter was increased significantly with skywave. So the usable range was reduced due to that interference, if you see what I mean.
And a final question from Doug. Why is Ayala differential GNSS being phased out?
Because the two reasons really. One is that with the multiple constellations, there is now no need for the integrity warning, which was its primary purpose. Because imagine you're approaching a harbor or operating, close to land in foggy conditions, and you're depending on GPS. If you get an error in timing from one satellite, that can give you an error of a couple of miles in your position. If you can't see where you are because of fog, you could easily find yourself running into the bottom of the mizzen, like Charlie Haughey did. The DGPS was primarily to provide integrity warning. It also provided an accuracy improvement as a secondary benefit. So the discontinuation of the system is due to the fact that with so many constellations now available and the proven reliability of space satellite-based positioning is no longer needed. And of course, you've also got the space-based augmentation systems like Egnos and Wasp and so on, which are becoming more and more proven and established as time goes on. And RAIM receivers are now available as well, the receiver autonomous integrity monitoring. So in other words, GPS receivers with built-in integrity monitoring. So the DGPS system no longer has a function.
Okay.
Thanks, Seamus. Your answers were quite comprehensive. I now wish to invite Chris Bruce to propose a vote of thanks. Chris.
Seamus, I was fascinated with your definition of navigation, a guide to where you are, where you want to be, and how to get back to where you come from. I think it's excellent. I was also amazed, really, at the progress that Marconi made. I think you said from about 1895 to the very early part of the century, he was going from 10-meter gap in his garden to crossing the Atlantic, which is just an incredible progress. I was thinking while you were saying this, your next job, I think, is to develop a dictionary of acronyms, because my goodness me, this is full of acronyms. It really is. I started trying to write them all down and I gave up in the end. I just want to say that as usual, you've given a very, very interesting talk. It really has shown the history of navigation and wireless and radar and all that followed on from that. And you know, one thing I often wonder about, we're told that in our grandchildren, or my grandchildren at the time, that they won't be driving their car, they'll all be driverless. Well, can you imagine the chaos when somebody switch the switch off and the GPS is gone, you know? I wouldn't be very happy with a driverless car on a long journey, maybe around town, but not any further. I think the other thing I want to say to you is that I had never realized the number of different, call them GPS systems. And as you say, what will happen if there was some sort of conflict? Say, what they'll do is, using my words, they'll scramble the signals so the missile will go off in the wrong direction. But I wonder if they'd be clever enough to make it go off in the direction they want. I don't know. I could go on, but I won't. I just want to, I would normally say, if I were to stand in a live room, is to ask the audience to put their hands together and give you an overwhelming clap, but I can't do that. So I suggest you'll see on the bottom, you can raise your hand and wave your hand and do that. Thank you very much, Seamus. Thank you. Very interesting evening. And I look forward to when we all get together again. Thank you.
Thank you.
Okay, thank you, Chris. And I'd also like to thank you personally, Seamus. Once again, I'd like to thank the IET members, the Engineers Ireland members, and other attendees who've joined us this evening. One of the few silver linings to this pandemic is that with the move to being online, we get a bit of additional reach with some of these presentations. So anyway, I've gained an insight into the topic as well, which is kind of so vital for both the delivery of goods around the world and hopefully all the travel that we're going to do as we emerge from these lockdowns. So I'll pass you back to Chris.
Thank you for joining us this evening, and I'm looking forward to seeing you at our next webinar. Goodbye.